pleasure to present my talk here. First of all, I'd like to thank Peter for his invitation. I talk about cosmology today, and the title is Asymptotically Einstein Universe. So, it seems that we are living in a very special time, or a very special period, as far as cosmology is concerned.
Excuse me, why not to the full screen mode? View, and full screen mode. Here.
So, we know that the universe is accelerating very recently, I mean, cosmic time, about 5 or 10 billion years ago, probably due to some unknown kind of energy called dark energy, which is repulsive, it's anti-gravity. And there is a very accurate measurement now, and cosmology has become precision science, as many people say. Physically, it is more special because the density composition and density structure of density structure, then we are living where this dark energy fraction is comparable to the matter energy density. So this is very probabilistically low because the matter decays very fast, whereas the dark energy stays constant. So only very short period of time, these two energy fractions can be comparable. And we are living on that very special period where these two energy fractions are comparable. So this is called a coincidence problem. Why are we living in this special period of time? And of course, at the center of this dark energy issue, there is this cosmological constant, which was first introduced by Einstein. So I will briefly talk about Einstein, the cosmological constant, and what is known as his biggest blunder. And then talk about accelerating universe, and then the fate of the universe, and then asymptotically static universe. So in this scenario, the universe does not expand or does not contract, but reaches a constant, the scale factor reaches a constant value. Therefore, realizing the Einstein's original universe, static universe. So let's talk about the cosmological constant and Einstein's biggest blunder. So after discovery of his general relativity, Einstein apparently applied it to the universe, and he probably at that time, most people, including Einstein, believed that the universe was static. So he has these two from his general relativity. Here A is a scale factor. You have these two equations. One is the energy equation, and the other is the acceleration equation. And from these, to make a static universe, you realize you have to have both of these to be zero because it's static. A has to be constant. And then from this first equation, you get rho is equal to minus 3p. And from the second equation, from vanishing of this, you have these conditions. So from this relation first, the energy density or the pressure is negative. So probably Einstein didn't like it. So he introduced a cosmological constant here. So we know that if you introduce a cosmological constant in the general relativity, the energy density changes by this amount, and pressure changes by this amount. So, for example, for a dust, where p is equal to 0, you could actually get a static universe from this equation if you replace by this. So here, the positive cosmology constant is 1 over AQ. So for small delta, we decrease by 3 delta A. So this will give you a net repulsive attraction. So to the universe glow with it, it will just keep on growing. If instead the universe contracts slightly, it will likewise produce a positive, attractive interaction, which makes it shrink more. So this static universe is unstable. Of course, after Einstein, people applied the general relativity to cosmology, and for example, Friedman established homogeneous and isotropic universe. And also in 27, Vigier, before Hubble's discovery, he actually proposed a expanding universe. So he found some non-static solution to Einstein equation. He supposed that the velocity of the galaxy is proportional to the distance, and he even estimated the proportional constant, which is now known as Hubble's constant. That apparently it seems that Vigier was the first person who concluded that the universe is expanding. And after that, of course, the Hubble discovered this law, V is equal to h naught. So the static universe was abandoned. And then we know we have this famous remarks by Einstein, which he told Gamow that much later when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological problem was the biggest blunder he ever made in his life. So that is the well-known remark. But cosmological constants now reappeared nowadays with the discovery of a accelerating universe. And probably Einstein will be proven to be correct again. I don't know what, because we don't know what is happening, but that the cosmological constant is the most promising one. So just maybe this is relevant or not, but so maybe he will be right again. The logic will get you from A to B. The imagination will take you everywhere. So that's the remark by Einstein. So let's talk about the accelerating universe. In 1998, 99, these people have discovered the universe is accelerating instead of decelerating. So how they found out this? They for many years the astronomer trying to measure this the deceleration parameter, which is given in terms of 0 means the current time. So it is given by this simple formula from the evolution equation. And if you just assume that the universe is made of matter and cosmological constant, you have a simple relation. So from this sign minus, probably you can think that they thought that Q was negative, so that this one was positive. So they thought that the universe was decelerating. But what these people have found is that the sign Q naught is negative. It means that the universe is accelerating. So how do they find about this? So they measure this type 1 supernova, which is good standard candle. In astronomy, it's very hard to import the distance from the stars. So, but the type 1a supernova is a very good standard candle, and this will give you distance versus redshift curve. So, in Hubble diagram, for example, the distance modulus, which is the apparent brightness minus absolute brightness, and the distance modulus, and the difference between the observed apparent peak brightness of supernova type 1a and its absolute peak brightness is plotted as a function of redshift. And from this, you can calculate the luminosity distance, and using this, what they found was that this curve here, they first found the supernova curve. Later, many other experiments, they found that omega lambda is almost 73 or 74%, and the dark matter is about 23%. So universe is made of almost all components of the universe are made of something that we don't know. We only know 4% of them. And this graph shows when the acceleration started. So if you plot this history of this Hubble parameter in terms of the redshift parameter G, you see that the acceleration has started about Z or 0.5 here. A dot is changing sign around at this point, so that around Z or 0.5 or 0.6, the universe has begun to accelerate. So, of course, the theorists now are trying to find what is the dark energy here. Why is the universe accelerating? So you can modify either the left-hand side of Einstein equation or the right-hand side of Einstein equation. So on the left side, you modify gravity. So there are many theories proposed. The first one is modified Newtonian dynamics. The second, another is the Scaratens theory, like the Franz-Dieter type theory, and FR gravity, where you replace this Einstein-Phillial action with an arbitrary function of R, and grain world scenario, DCP scenario, Cartesian model, and Gaussian gravity. Seems like on the right-hand side, you have these many theories. Quintessence, we introduce a scalar field. Of course, the problem is that we have never observed a scalar field yet. But the LHC scalar is different from this. So this just decays to gamma. So, and also you have phantom, which has the negative kinetic energy. It's necessary to get the data. For example, the equation of state is minus. It is less than minus 1. So, with that equation of data, you need the phantom, which has negative kinetic energy. The K essence, kinetic energy, you modify the energy of the scalar field, not just the standard 1/2 phi of the square, but it's very complicated function of phi. And this gets, and there are many theories. But all these things, still, the lambda CDF model is the most promising one. But it has some problem we all know about. Okay, so what is the lambda Koldak model? So if you look at the evolution equation of this scale factor here, the Koldak matter is dust, so it behaves as 1 over AQ. But the lambda here, if you look at the lambda, the energy density, this one is energy density, is about 9.8 times 10 to the minus 30 grams per centimeter. It's a very small number. So why is it so small number? Because the natural scale in Einstein gravity is Planck mass, and compared with the Planck mass, it is about 10 to the minus 122 orders lower than the natural scale of gravity. So so this is the so-called cosmological constant problem. Why is this constant so small compared with the scale of this? So this is one of the fundamental problems. Anyhow, just you accept that the small number as a reality. Then if you look at the energy density here, this is now the cosmological constant. Energy density is dominating, but earlier times the matter was dominating. But the matter energy density goes very fast, and cosmological constant is just the constant, so it stays the same. So we are living in a very small area here. So that's dominant, the energy dominance. First, the matter was dominant, but now the cosmological constant, dark energy, has taken over. If you look at the same diagram in terms of energy fraction, at first the fraction was very small, but it is now almost dominating. The matter density was dominant earlier, but it is now has decayed much faster. So, even though the lambda CDM is now established almost as a standard model, but there is always this problem, the cosmological constant problem. Why is lambda so small? So one proposal is just to take it as a constant of nature. Doesn't matter whether the value is very small or not, it's just a constant of nature. Very small. Why is it? Who knows? God knows it's very small. And then you just say that it reflects the intrinsic nature, intrinsic property of space-time. But the problem is not so simple, because there is always this vacuum energy. So if you look at the left-hand side and right-hand side of Einstein equation, there is a very big disparity, actually. For example, if there's nothing, then the left-hand side of Einstein equation is a flat space because space. But in the right-hand side, we know from quantum field theory that the vacuum is not without anything. I mean, the vacuum carries its own energy. How much energy does it carry? For example, you can calculate the energy density vacuum, for example, to be omega k of this much. If you introduce a cutoff here, T00 becomes about 10 to 70 or G before. On the left-hand side, the observed value is like 10 to minus 44. So the discrepancy of 122 orders of magnitude. So this has been a problem, and still a problem. And this is maybe a really fundamental problem. So how do you explain this discrepancy between the left-hand side and right-hand side? But apart from these, people I think have tried to propose a theory that the lambda is zero, quantum mechanically or classically. So, for example, you know that in Hawking, 1984, proposed that the apparent cosmology constant is not zero, but zero is by far the most power variable in the waveform of the universe. 1987, Weinberg, using the anthropic principle, said that the cosmology constant must be zero to within 10. It's not absolutely zero, but it must be zero within one part in roughly 122, or else the universe I would have dispersed too fast for stars and galaxies to have formed, or else would have collapsed or penetrated. So it's for human beings to be here, we need this amount of there are many other proposals. But all these things is set aside this problem, the huge vacuum energy density. So when you talk, when for example in quintessence model, you assume that there is a principle that the positive vacuum energy and negative vacuum energy cancels, and the energy density decays probably to zero, but if we are not there, it will eventually be zero. Okay? But anyhow, this is a fundamental problem. So another way of looking at this is get rid of this cosmology constant that is this symmetry argument. For example, Padmanabhan has proposed that there is a difference between these two, gravity and matter sector. For example, we all know that adding a constant to the classical Lagrangian in the matter does not change anything. Okay? So it's constant, the equational motion same. So adding a constant to the matter sector is a symmetry of the matter sector, and it's a symmetry of the matter sector. But general relativity does not respect symmetry, because if I add the constant here, it changes the geometry. So there is a fundamental difference between matter and the gravity sector. And he proposed that the metric is not a fundamental dynamical variable, but it's an effective description of space-time at macroscopic scales. In this case, the gravity arises emergent and long wavelength phenomena, and can be described in terms of fundamental theory. So specifically what he did was that this gravity can emerge with a normalized vector field. And then the gravity, the theory is explicitly embedded in the shift of the energy momentum tensor, and that means that any bulk cosmology constant can be gauged away. So this is one way of getting rid of the cosmology constant. But I think this is the kind of approach that may help in the symmetry argument. So now, let's talk about the fate of a universe. For example, for lambda CDM, the scale factor behaves like this. So this one is a power law at early time. The sine hyper is like t. So it's a power law expansion, and at break times it goes like exponential expansion. So in this case, the universe will expand indefinitely. The phantom model, however, has the feature of increasing, but it develops some singularity. So when the universe has evolved enough so that you can direct this matter energy density which it decays, then the energy at that region, the scale factor can be written in this way. And omega for phantom model, which is the equation of state, is less than -1. So when t is equal to ts, at diverges. Not only at diverges, but h also, the Hubble parameter diverges and curvature diverges. So everything diverges, and they call it the Greek singularity. But maybe here that when this curvature effect becomes large, then quantum effect may come in. Another possible scenario is big crunch. In this model, the dark energy dissipates with time, and universe contracts in a big crunch as in the cyclic model. Another fate without this dark energy model is that the singularity can even occur at the Friedman type universe. So this is what is currently known result of the fate of the universe. One is big rip, where everything will become torn apart, singular, and just end up in a big singularity, or the constant dark energy like lambda lambda CDM will go an indefinite expansion, or big crunch, like the dark energy dissipates and the matter will dominate again. So what I'd like to talk about is the possibility that the universe, the scenario is that the universe is now accelerating, but somehow it will reach a constant value. Okay? So that's asymptotically static universe. So is this possible within the theory context? So in order to see that, you just look at again the acceleration equation. So here, the acceleration, for acceleration to occur, for example, rho plus Vp has to be less than 0. For deceleration, rho plus Vp has to be greater than 0. To reach a asymptotic state, this has to be 0. It means that there is the repulsive force and attractive force has to balance somehow. So, for example, in quintessence model, rho is 1/2 pi dot square plus Vp is equal to pi dot minus V. In the phantom, the energy, kinetic energy is negative, so rho is minus 1/2 pi square is minus 1. So the components which contribute to the on the accelerating side, rho I plus pi, each index means the each component is that on the accelerating side you have this one, which is like omega is equal to 1 component, and positive cosmology constant, because for positive cosmology constant, rho is equal to minus p, that this is negative. And I'm sorry, so that's because I'm sorry, this one should be called continue to come down. This one is decelerating, and this one actually minus 1/2 is accelerating. So this should change the phrase. And also V is also accelerating. So this one and this one. But the point, one thing is that now lambda core documentary is in terms of a positive V, but I talk about negative cosmology constant, and then in negative cosmology constant, then it is on the decelerating side, okay, and then core documentary. So the asymptotic state universe can be realized if there is a balance between this attractive force and the but we don't know which one the exact position. So in asymptotical state, we investigate the universe, which is neither accelerating nor decelerating, but becomes asymptotically static. And but we don't know exactly what kind of proportion they should come in. So we take the strategy that we first assume the AT, which has the desired property. It means that at t equal t naught, the universe nowadays is accelerating, and when t goes to infinity, then it will reach a constant value. So it will accelerate, and at some time it will begin deceleration again, and then it will reach a constant value. So the model, so what I do is that we'll assume this from the beginning, and put this thing into the evolution equation, and determine the energy densities. So the model we took is this model, this somewhat modified quintessence model. And here Sm is the matter action, which we assume to be a cold dark matter with omega. Now the Einstein's equation are given by this. The H is the Hubble parameter, and the density is this, and the field equation satisfies this. So of course there is no analytic solution. You just have to resort to the numerical analysis. So as I mentioned, we just plug in this Anjat and see what kind of energy densities you get. Also for scalar field, you just assume this simple form. So in order to determine the constant, we need you have to be at least consistent with the current acceleration. So A at t naught, the now, has to be A naught. And H at t naught, which is the Hubble parameter at current time, is not to be 1 over t naught. So from these two equations, you get A and B, where M is A naught over A infinity from here. So we have two parameters to fit into the observation. One is this, what is the final scale factor of the universe, and the other N, which is the when does related to when does the deceleration begin. So now you have this more things to plug in. Also, you have this one observational fact that the equation of state for the scalar field, which is given by this one, is within the range of minus of this range. So if I just plug in, you have this curve here. So every point inside this blue band are around. Okay. So M here is, as I said, is the final scale factor. So if you, for example, M equals 3, our universe will grow 3 times of current scale. N. So A here now is accelerating, and then at some time, the T star it begins deceleration, and then reaches constant value, and H will decrease, and the potential is the potential is dominant. Okay, but it decays, and the matter decays, and omega. So in the end, there is a balance between the potential and the matter that achieve the static universe. But this model turns out to be unstable because the effective equation of state omega diverges, and also the kinetic of the coefficient of the kinetic energy, this omega, which was the coefficient of the kinetic energy, this one, this becomes 0. It has to pass from negative to positive to negative. So this is unstable. So we
7 minutes, 6 minutes.
So actually, you can replace this model with two scalar fields to avoid this singularity. One is crossing of this omega. You have to make this omega positive in both cases or negative. So the original omega you can replace by two omega. So this one is the scalar field. This one is the phantom field. So in terms of these new two scalar fields, we have this one and this one. This one is scalar. This one is a phantom.